In this final video of Lesson 1 from Part 1 of Unit 3, we're going to talk about the logarithmic function specifically. And in this introduction, I want you to know that this logarithmic function was developed to be the inverse of exponential functions. And when we encounter exponential functions that can't be solved easily, we rely on the logarithmic function. For example, if I were to try to answer part A for m, well, that's easy. I could multiply 1.2 times itself 3 times and obtain the result for m. And we have m that's equal to 1.728, as seen here on our TI calculator. For part C, well, this is a little bit more challenging, but it's something we can do with our regular math. A to the fourth power is equal to 24. Well, in order to isolate the a and to undo this fourth power, we would need a fourth root, or a radical with a base of 4. And now the fourth root of 24, we can do that on this calculator as well. We just need this command here above the exponent key. So we'll press Control Exponent, and we'll specify that we want the fourth root of 24. And if your calculator gives you an answer that you don't expect or you don't want to deal with, if it's a precise answer, simply press Control, then Enter, and that'll give you the decimal equivalent. Now, I prefer 4 decimal places for accuracy, so if we round to the 4th decimal place, we'll call this 3A4, 2.2134. 2.2134. Now here again, both of those solutions were obtained by using a basic calculator, but the one in the middle now, that's a little bit different. We also have to remind ourselves here that the letter E in this case, E is a number, 2.71, I think 8282. And that number raised to some unknown power is equal to 9. And just for argument's sake, let's make this a little bit easier to work with. Let's say that I've got 4 to some power equals 9. 4 to what power equals 9? Well, it's not like part C where I can take a radical on both sides. If I were to try to take the bth root, if that was such a thing, I'd have to specify what the index of that radical was, and we don't know that answer. That's in fact the number that we're looking for. Also, if the base happened to be a nice number like 3, well, that's something we can interpret because we know that 3 squared equals 9. And if 3 squared equals 9, then b would have to be 2. But that's not the case here. That's not what we were given originally, and that's not always possible. We can't always get a nice solid solution. And for that reason, the logarithm was established and developed. The logarithm with a base of a evaluated at x is equal to y if and only if x is equal to a to the power of y. So in other words, if we are looking for some y value, some calculated result, this is an output of the logarithmic function, and x is the input of the logarithmic function. And you'll notice that x over here, much like we described with inverses, is the output of exponential, and y is the input of the exponential. And as I said in another video notes for this particular lesson, when we can switch the inputs and the outputs of a function to another, then we are doing so in its inverse. So again, we're saying that the input of one function is the output of the other, and the output of that function is the input of the other. The inputs and the outputs have switched. Now, just some ground rules that we have to be aware of when we use the logarithm. The base of the logarithm, this subscript letter here, must always be greater than 0. It can't be 0, and it must be greater than 0. It cannot be negative. And also we don't want that a value ever to be 1. The reason for that is or the reason for both of these is when we rewrite a logarithm as an exponential, it either becomes unpredictable in the event of a negative base, or it becomes just not interesting when the base is 0 or 1. Additionally, this note goes on to point out that x, the argument, we sometimes call it the input of the logarithm, must also be positive. The domain of the logarithmic function only works with positive x values. So the questions here are actually asking us to change the exponential statement into a logarithm. So we're not actually going to solve them here, but we are going to rewrite them. And I want to point out that each of these exponential phrases can be, and should be in this case, rewritten as a logarithm because of their inverse compatibility. So the base of the logarithm ends up being the base of our exponent becomes the base of our logarithm. And the output of our exponential over here, across from the equal sign, becomes the input of the logarithm. And the input of our exponential becomes the output of the log. Let me show you what I mean. If I were to rewrite this exponential as a logarithm, I'd use the logarithm notation with a base of 1.2. I'd evaluate this logarithm at the unknown number, m in this case, and the result of this logarithm would be equal to 3. Now again, we're not solving the exponential here. I don't want a solution to the exponential. I just want you to practice with the vocabulary and rewrite the exponential as a logarithm. Here's another example. The logarithm's base is the same as the exponent's base, so we'll say a logarithm base e. We'll evaluate at the output of the exponential, which becomes the input of the log, and the output, or the result of the logarithm, was the input of the exponential. So now here's something I can actually bring to the calculator. I didn't know what b was earlier, e to what power equals 9. Well, now I've got something. If I press the logarithm key and specify that I want the base of e, whoops, not the natural log, let's do base of e. I'm going to use e to the first power here because this calculator expected an exponent with the letter e. So e to the first power is our base. We evaluate this logarithm at 9, and I'll press Control Enter because I want to see what the decimal is right away. And evidently e to the 2.1972 power would equal 9. Let's check that out. E to the 2.1972457734 equals, that's pretty close. So we lost some accuracy due to the rounding, but I'll say that e to this power does indeed equal 9. So that's a good way to rewrite the exponential and how we can use a logarithm to solve that exponential. And then lastly over here, the logarithm base a of 24 equals 4. And usually at this point I tell students about the loop rule when rewriting logarithms. If you always start at the base, much like an exponential starts with its base, and you loop across the equal sign and come back to your argument, if you imagine this loop or this cycle here, that would be one way to rewrite your exponential. So we're starting with the base a, raise it to the power of 4, which came from across that equal sign, and loop back to 24, a to the 4th power equals 24. This implies that this logarithm is indeed a way to rewrite the exponential. So let's use that concept to answer these following questions without a calculator. We need to find the exact value of log base 2 of 16. Now, this logarithm concept is pretty new to you, and I wouldn't expect you to know this answer without a calculator. But let me share something with you. If I had an unknown like x, and I said find x, solve for x, well, now we can use that rewritten rule or way to rewrite this as an exponential and solve for x. Follow the loop. Start with your base of 2, loop across the equal sign, and come back to the 16 and write your exponential. log base 2 of 16 equals x is the same as writing 2 to the x power equals 16. 2 to what power equals 16? Now this is a nice one. 2 to the 4th power would equal 16. So I know the solution to this logarithm is 4. Here's another. Log base 3 of 1/27 equals some unknown value. So if we rewrite this using the loop rule, we can say 3 to what power equals 1/27. I'm going to make a note here that 27 is the same as 3 to the 3rd power. And now that's sitting underneath a denominator, or as a denominator under the numerator 1. And if I didn't want this fraction anymore, if I wanted to bring this exponent of 3 back to the top, all I have to do is change its exponent from a positive 3 to a negative 3. And now we can see that the equation is written with common bases. If 3 to some power is equal to 3 to the negative 3rd power, well, as you might have guessed, x then must be negative 3. So therefore, log base 3 of 1/27 is equal to negative 3. So now with slightly more complicated examples, let's see if we can use that log rule here as well. We can start at the base, loop across the equal sign, and that would be equal to this argument. Now when the argument gets to be a little bit larger than a single number or a single letter, we do usually write it inside of parentheses, and that's what's done here. So we're saying that 3 squared is equal to 4x minus 7. That's what this logarithm really means, or another way to rewrite it. Well, 3 squared, of course, is 9. We can add 7 to both sides and say that 16 is equal to 4x. Therefore, x is equal to 4. And then finally, part B, x raised to the power of 2 must equal 64. So we're going to say that x squared is equal to 64. And you'll recognize that we can square root both sides. But since we're bringing the square root to this problem, we have to be prepared for 2 solutions. And in this case, I would say only one of them is good. This one here. Because remember the requirements with logarithms. With our base power a must be positive, and it may not be 1. Down here, our algebra led us to believe that our base, even though we're calling it x, it's in the position of where a was in our definition. This base must be positive. This is what we call an extraneous solution. These extraneous solutions pop up from time to time, especially when dealing with radicals or rational functions, but also in logarithms as well. So we've always got to be on the lookout for them. Now the very last thing I'll remind you of, hopefully you've seen this before, is this phrase ln x. This stands for the natural log of x. Natural log. And natural log is written with ln. There's such thing as called a natural base, and the natural base is that letter E that we saw before. So in my calculator, a moment ago I used a logarithm with a base of E, and that was a little bit difficult for the calculator to use because this is actually pretty unusual for the calculator to evaluate. Anytime that we use a logarithm that has the base of E, instead of using this traditional log notation, we use the natural log notation. So ln is what we use for natural log. If log base E of 9 equaled 2.19, then the natural log of 9 will also equal 2.1927 or 197. So this result and this result are the same because this phrase, log base E of 9, is the same as the natural log of 9. And that's what our notes over here are saying. Any logarithm with a base of E is written as just the natural log, ln, with the same argument, in this case x. And again, a reminder here, the natural log of x, even though there's no base written here, it's a logarithm with no base written. In this case, we assume that the base of that logarithm is the number e. So I hope that provides a little bit of clarity with the logarithms, and if you're starting your Math Excel work, this should hopefully get you going in the right direction. If you have further questions, please let me know. Thanks for watching.